Other than gravity and normal force, the next most common force we deal with in our everyday lives is friction. And friction is really just a resistance force. It's caused when two surfaces are in contact with one another, and there is some kind of resistance to an attempted motion that's going on. But we should start by actually breaking friction into two different categories. There are two main types. The first kind is called static frictional force. And it exists anytime you're trying to move an object from rest. But that static word means that it's not moving. It comes from the same root word as the term stationary. The object's not moving. And so if you're pushing on an object really hard or pulling on an object really hard, but it's not moving, it's because there's a force resisting on your pulling motion. That resistance force is the static frictional force. And so someone is trying to pull this box in this direction forwards, but there is some frictional force between the box and the floor that is in the opposite direction opposing that force. And because those forces can rise to be equal to one another, they'll completely cancel one another out, and we end up with an object that is completely stationary. Now, the reason why this friction exists is better understood if we look a little bit more at the microscopic level. And so this diagram here is blowing things up for you, imagining that you could zoom way into the microscopic level of what's going on between the bottom of the box and the top of that surface that it's sitting on. And so there are all these little bumps and grooves, and you can kind of see that in static friction, a lot of those bumps and grooves get locked into place. And so it kind of locks those pieces in, and so it becomes more difficult to pull your way through. We've got some areas, for example, here, where it's right inside of the groove, and it's hard to get outside of those grooves. And it all happens at a very microscopic level, but even small microscopic particles can still be enough to apply certain forces that oppose our motion. The other kind of frictional force then is called kinetic frictional force. And just like in our kinematics unit, that kinetic word means motion. So it's the friction experienced by something that's already in motion. And so you've felt this force if you've ever slid along the ground or pulled a sled along the ground. So the object is still able to move, but you are still feeling a force working back against you, making it a little bit harder to pull on that thing or to slide something across a surface. And that's a little bit different than static frictional force. As you can see in this little microscopic diagram, it's not so much that things are locked into place, but if we just look at that area when they're meeting, there are still lots of little bumps that are interacting. And they won't necessarily catch and lock in place like in static frictional force, but they'll still bump and grind and hit against each other in a way that will apply some small amounts of force that will work back against our motion. But this would be a case where this object would still be able to move with some velocity forwards, even though there is still that frictional force acting. And in that case, we call it a kinetic frictional force. So now if we imagine applying a lot of force to, let's say, a box on the ground and trying to pull it forwards to make it move, we actually, in certain cases, might see both static friction and then eventually kinetic friction as well. So let's start with the simple case of static. So when the box is originally stationary, it's feeling some static frictional force. And the reason that is because of balanced forces, once again. So there's the box on the ground that I'm trying to lift, and that little dot just represents its center of mass that all of the forces are going to be acting from. And we'll imagine that I apply some force, which I'll just call F with a little a, and that's a commonly used term just to mean applied force, Fa. That's my pulling force. But if the box isn't moving, just like we kind of saw with normal force balancing out gravity, we must have some force going back in the opposite direction that balances that out. And in this case, that force that's going back in the opposite direction is Ff. It's a frictional force. More specifically, though, we remember that it's the static frictional force. So always remind yourself of that. And if that's the case, then I'm going to borrow something we used in a previous note and use those little tick marks. Again, those tick marks are indicating that even though I may not have drawn them to be exactly the same measurement, I'm trying to indicate to anyone who looks at this diagram that FA is supposed to be equal in magnitude to FF, but just opposite in direction. What about if I pull even harder, though? So let's imagine that I pull even harder, but the box still doesn't move. So I have my box, I apply an even stronger force, so I'll draw it as an even larger vector, but the box still doesn't move. Well, what happened? Well, the only reason we can explain why it didn't move is because there must have been a force that was equal to it in the opposite direction. So that means there must have been a larger frictional force as well. And now again, to indicate that, I'm going to use just 2 tick marks. But again, those tick marks are still just trying to indicate that those forces are equal to each other. And so if the applied force grows, what we're seeing is that the frictional force, the static frictional force specifically, will grow to match it. And I can even take this one step further and go even a little bit more extreme. What about if I really pull even harder, but it still doesn't move? Then I just have a very strong frictional force that must be opposing it. But we know that that can't go on forever. There must be some breaking point, no matter how heavy an object is and how rough those surfaces are that are interacting. Eventually, this box is going to start to move if we pull hard enough. As soon as it starts to move, it will still experience friction, but it will experience kinetic friction now. So in this case, once it finally starts to move, our diagram of the box forces will look a little bit different. Now we'll have some very large applied force to make this all happen, because we've now seen that we would need to apply a very strong force to get it moving, but then it still will feel some force resisting the motion, but just not enough to completely cancel out the applied force, which means it'll just feel some amount of force that's less than the applied force. And so that's something you can make note of specifically in your notes. What we're seeing there is that FA is much greater than FF. And that allows the object to be in motion. Specifically, as we'll see more when we get into more free body diagrams in our next note, we'll talk about how that stronger applied force will not only make it go into motion, it'll specifically cause it to accelerate. So one thing we can summarize from that then is that the static frictional force is always larger than the amount of kinetic frictional force between any 2 materials. And at a certain point, if the static frictional force is going to be overcome, or if it's eventually overcome, it'll be easier to keep that object moving from there, because the kinetic frictional force that it's feeling is less than that static frictional force that was working back against it originally. Now, in future notes, we're going to work on some situations when we can actually calculate frictional force, and we'll do a little bit of this in class as well. If we want to actually calculate how much frictional force something has, we can use the following formula. And it actually depends a lot on normal force. So first off, the FF is what we're using to represent friction, but we know it's a force, so it's measured in newtons. That fancy letter below it I'm going to save for a second and just point out that we also have normal force, again still measured in newtons. And think for a bit about why normal force would be important. Remember, normal force is some measure of how strongly a surface needs to push back against anything that's pushing against it. And so if surfaces are really strongly pressed together, if there's a very strong force that's pushing something into the floor, for example, then the floor must be exerting a very strong force back. So that normal force gives us some idea of how much we're pressed against the surface, or how much the surfaces are pressed together. That's why we include normal force as part of this. And so if you have a larger normal force, it's because the surfaces are really strongly pushed together. And if you have surfaces really strongly pushed together, As you can imagine, if you push your hands together and rub them really hard, you get a very strong frictional force, a strong friction effect happening. But it's also going to depend on what the surfaces are. So obviously, pressing down really hard with your foot on concrete is very different than pressing down very hard with your foot on ice. And so the relationship between the two different materials is all condensed into one special value called the coefficient of friction. And it's actually a fancy Greek letter mu, which in class I'll talk a little bit about some easy ways you can write the Greek letter mu, but it's kind of like drawing a cursive letter U with an extra tail to it. So we draw this big extra tail, and then we draw a handwriting U, and it kind of ends up looking a little bit like an M with this extra tail hanging off. That's the Greek letter mu. And we use that to represent something called the coefficient of friction. The coefficient word just means that it multiplies out in front of something else, specifically the normal force in this case. But it's a special value that is usually between 0 and 1. There's some special cases that can be greater than 1, but it's usually between 0 and 1. And essentially, it's giving you some idea of what percentage of the normal force is equal to your frictional force. So if I, for example, had a mu value of 0.5, that would mean that my frictional force would end up being exactly half, or exactly 50% of my normal force. Because when I take 0.5 and I multiply it by my normal force, I'll get something that's exactly half of my normal force. So that value for mu, again, really just gives you some idea of what percentage or what fraction of the normal force will equal your frictional force. A final thing we can do then is just look at how we analyze these units and do a little analysis there. So if we've got a force of friction, we know that needs to be measured in newtons. And then we've got some value mu, which I haven't even stated a unit for yet, so I'll leave that blank for now. But we know that it's being multiplied by the normal force, which also is measured in newtons. So now we need to think, what would the unit for coefficient of friction actually be? And this is where it's a little bit tricky, but almost because you might overthink it. The unit for the coefficient of friction does not exist at all. It is what we would call unitless. And the reason is, well, you can see from unit analysis why it works. We already have newtons being part of normal force, and we get newtons in our answer. So what, again, the mu really represents is a special decimal number, which you can kind of think of as representing a percentage, to give us the percentage of one force that will equal this new force, the percentage of the normal force that will equal the frictional force in this case. As I said, in class and in future notes, we'll see some more specific examples of how we can actually use this to help in our problem solving from here on out.